Hey, it's Nick Luciano, and today we're going to talk about diatonic set theory. As we go through this, there's one question I want you to keep in mind. Why is the diatonic scale so special anyways? So to start, let's talk about the basics. Theorists dealing with diatonic sets will often use numbers to represent pitches, much like theorists dealing with atonal sets. However, instead of using 12 numbers to represent the pitches, diatonic set theorists will often use 7. These 7 numbers measure the generic intervals between events. For example, a third is a third no matter how many half steps it contains. We'll typically see intervals such as C to C, so a unison, is 0, C to D, a second, is 1, a third is 2, a fourth is 3, and so on and so forth. We can use these numbers to construct chords also. For example, our C major chord is constructed by 2/3, which is represented by the 2's in 2-2-3, and then a fourth to get us back to the octave, which is represented by the 3. These numbers are always going to add up to 7. Many of the interesting features of a diatonic scale come from the fact that it is a well-formed or generated scale. This is a term meaning you can get the pitch collection by repeating one interval, in this case the perfect fifth. This is demonstrated here. By only moving the interval of a fifth, starting on F, I was able to produce all of the pitches that appear in a C major scale. I think that one of the coolest traits of the diatonic scale is that it's a deep scale. To explain these, I need to explain how interval vectors work. Interval vectors were used by Fort in his atonal set theories alongside the pitch class sets. They indicate how many of each interval a set contains. Our diatonic set, 0, 1, 3, 5, 6, 8, 10, also known as set class 7-35, has the vector of 2, 5, 4, 3, 6, 1, meaning that it has 2 half steps, 5 whole steps, 4 minor thirds, 3 major thirds, 4 perfect fourths, and 1 tritone. Notice that no number occurs in the vector more than once. Each interval class occurs a unique number of times. This is the definition of a deep scale. Deep scales are often generated and only occur in collections that contain n divided by 2 or n divided by 2 plus 1 tones, where n is the number of pitches in the universe the scale exists in. So, in the 12-tone universe, 12 divided by 2 plus 1 equals 7, or the number of tones in the diatonic scale. Furthermore, theorists have found this property in microtonal systems as well. For comparison, here is a 16-note scale derived from a 31-note universe. Notice that the vector in the bracketed area does not have a repeated number. Obviously, we can't use the terms half steps as we know them. These numbers represent a 31-note universe's equal divisions. We've touched on the fact that we can use generic intervals in diatonic theory, but we also can use the specific intervals as well, those dealing with the number of half steps spanned. This is where major, minor, perfect augmented, etc. come in. Since the diatonic scale contains exactly 2 specific sizes for each generic interval, it is said to have Myhill's property. Sometimes, however, the generic and specific sizes don't agree. For example, we have difference, which is where we have the same generic size but different specific size. An example of this is C to E and D to F. Both are thirds, but they span different amounts of half steps. There's also ambiguities where we have the reverse. We have the same specific but different generic. So B to F and F to B are examples of this. B to F is spelled as a fifth and F to B as a fourth, but they both span 6 half steps. There's only one ambiguity in the diatonic scale between T and Fa. There are also contradictions. These are where 2 pairs of ordered pitch classes contradict one another. So we have B and A flat, which is spelled as a second but spans 3 half steps, and B sharp and D, which is spelled as a third but spans 2 half steps. These do not naturally occur in the diatonic scale. We're going to wrap up by talking about variety and multiplicity. There's this concept called cardinality equals variety, where the number of notes in a collection is the same as the number of possible arrangements of the notes. So triads have 3 notes, and so we find them in 3 different versions in our diatonic scale: major, minor, and diminished. The same applies for 7th chords. They contain 4 notes, and we find them 4 different ways. So this leads us to structure implies multiplicity. This states that the number of steps around a generator, in this case a circle of fifths, between the members of a collection implies the number of possible arrangements that can be constructed. So what does this mean? I've constructed a line of fifths here. They're not perfect fifths, mind you, but they are fifths. And I also built triads on all of the members of our diatonic scale. So the distance between C and G on our line is 1. The distance between G and E is 3, and the distance between E and C is 3. So the result of 1, 3, 3 reflects that we have 1 diminished triad, 3 major, and 3 minor. This doesn't tell us where these collections are located, only how many is implied. So going back to cardinality equals variety, CV tells us how many types there are, and then SM tells us what those types are. So all of this relates back to our question: why is the diatonic scale so important anyways? It's because all of these neat properties apply to our diatonic scale. That's all for today. Thanks for watching.